Okay. I think we can slowly start again for the third lecture of the week. Just two clarifications. I just wanted to clarify two things of the two lectures before where I missed things. So the Larmor radius is defined indeed with the gamma factor, and from the equation from which I derived it was in the fully relativistic case. And then you can have the gyro radius when you go into the non-relativistic case. Okay, and then of course in the definition of the power of the inverse Compton, there was a vector on the area. Okay, so this should clarify the little thing of yesterday. And so today we can go ahead with the main processes that involves protons, because mostly the things that were relevant for continuous energy losses, so synchrotron and inverse Compton, are actually important for leptons because of the dependence on the electron mass. So they rapidly are very inefficient for hadrons, and this you can realize by looking at the dependence on the Thomson cross-section, for example. So in the classical limit, the cross-section goes as the charge divided by the mass squared. So this is an efficient process as long as the mass of the particle is light. And as soon as you start to look at hadrons, then the probability of interactions through those gamma processes that we have seen yesterday then becomes less efficient. So that's why we don't typically talk about inverse Compton on protons, for example. However, what happens is that for protons at ultra-high energies, what you start opening up are channels for inelastic processes, because the protons also experience nuclear force. And so those are the processes that are the most relevant for energy losses of high energy protons, and that we will see today. So let's start considering the interactions that you can have between protons and photons. And typically those are processes that are yet collisional. So you have scattering processes, but you have that the protons during the interaction with the photon basically lose a lot of energy or completely get distracted by the interaction. So those are like catastrophic loss processes, where those processes are characterized by a factor which is called inelasticity, which describes what is the energy lost by the primary particle, so in this case the proton, during the interaction. We'll see that most of the processes that we will see today are indeed have quite a high inelasticity. So let's then start with the photo pion production, which is the first of the processes described here. So what will happen is that you have a proton, cosmic ray proton, that is is encountering photons from a radiation field, and it can produce other hadrons, or protons or neutrons, and there is an associated production of pions. So then you can have neutral pions if you produce protons, or charged pions if you have neutron production. So first of all, as we have done in the other lectures, so this is a process that needs a threshold to occur. So there is an energy cannot occur for any energies of the protons. So we are interested in understanding what is the energy threshold for the proton in order for this production channel to be open up. So let's consider proton-proton that goes into proton pi 0, for example. And so again, we can consider the center of mass energy in the initial and final state, and we want to be able to produce the final states at rest. So is again what we have seen yesterday. And in the initial final state, you will have the dependence on the proton energy, the radiation field energy, and the angle between the radiation and the proton. So by now, you should be at ease with that, and this is probably the last time that I'm writing that explicitly, where psi is the angle between the direction of flight of the protons and the photon. So then we can derive what is the energy that the proton has to have in order for this reaction to occur in the center of mass. And is related to the mass of the final states and the kinematics of the process, right? So if you have head-on collisions, so then you can get rid of this factor, and you can consider typical energies of the CMB of about 10 to the minus 4 electron volt, and so you get that the energy threshold for CMB upscattering is about 10 to the 19 electron volt. So this is an interesting number, because if you remember the all-particle proton spectrum of cosmic rays, then you remember that the cosmic rays do span like 20 order of magnitudes in energy, right? At the very highest energy, you can reach 10 to the 19, 10 to the 20 electron volt. So this threshold energy gives you directly an horizon for the proton. You can rewrite that as a function of the radiation field. And so you can see that, again, depending on the radiation field of the photons, which can be either the CMB or the extragalactic background light, you can produce, protons can open up this production channel only for a given threshold. So this has kind of two implications, this process, because on the one hand, it means that there is an horizon, like a cutoff that you expect in the proton flux, because above this energy threshold, protons will start to disappear because they open up the production into pions. So this sets what is called the GZK cutoff. I have to read it because it's Grisen, Zazepkin, Kutzmin, so the three authors that introduced this. So this is a cutoff that you expect in the flux of ultra-high energy cosmic ray protons. And it justified the fact that above more or less 10 to the 19 electron volt, you do not expect to detect a sizable flux of ultra-high energy protons. So then if you find protons or particles at ultra-high energies larger than 10 to the 19, then these can have profound implications for, again, cosmic ray propagation in extragalactic environments or new physics. And is also related, so this is for protons, but of course, do not forget that at very high energy, we also have higher nuclei, in particular iron. So this cutoff is valid for protons, but it will change because the threshold does change if you have heavier nuclei. So if the composition of the ultra-high energy cosmic rays is dominated by iron instead of protons, then you might expect a different intensity of the flux at very high energy. And this is one of the ways in which you can interpret the fact that we do measure cosmic rays with energies higher than this GZK cutoff. Yeah. Yes, so are the names that I now am writing of the three authors. Okay. Okay. So how this process, as I mentioned, is strongly inelastic. So the inelasticity is about the mass of the final state divided by the mass of the primary, and is let's say 15% more or less. So it means that the energy of the proton gets depleted, and the energy of the final pion, we will see, is related to the energy of the primary proton. So then how often this process does occur? But this is set by the cross-section. So the cross-section for this process mostly goes through the production of a delta resonance. And this is so this is the cross-section as a function of energy in the lab frame for either production of proton or neutron. So for the two different final states here. And there is the production of the delta resonance, which has a mass of about 1.3 GeV. So once you have like this process and the cross section, what you can then do is to ask yourself, okay, but what are the energies of the photon fields that are relevant for this kind of process? So then I said that there is the CMB, but more in general, we would like to understand what typical energy of the photons can produce ultra high energy pions. So if we apply again the conservation of the center of mass energy in the proton rest frame, we can derive that the energy of the photon in the proton rest frame should be larger, because this is the threshold, than the mass of the pion plus the mass of the pion squared divided by the mass of the proton. So then if we use the mass of the neutral pion, this is about 145 MeV. So then we go into the lab frame, and so the energy of the photon in the center of mass frame is related to the energy in the lab frame by this relation, and this is the gamma. So is related to the velocity of the proton. So from here we see that if we have like energies of the photon fields that are of the order of the CMB, so 10 to the minus 4 electron volts, then in order to meet the threshold for production, then we need the gamma factor of the order of 10 to the 6, while if we consider like radiation field of the, for example, ABLs, or so optical or infrared that are at higher energies, then we need lower gamma factor, Lorentz factors of the protons. So since there is this variation in radiation fields, then this allows us to get the proton interactions with pion production for different values of the proton primary population. So that means that you have a variety of protons that can give you the final pions. The EBL is the extragalactic background light, so it's the radiation field in the extragalactic environment. So there is also another process which can give you interaction between protons and photons, and this is the more common pair production, which is not the same as the thing that we have seen yesterday. That was with radiation, but you can have the same effect with protons, but now you have, again, an energy threshold for the proton for this process to open up, which is similarly derived. And for the CMB, so epsilon of the order of 10 to the minus 4 electron volt, this energy is 10 to the 17 electron volt. So to proton-photon interactions, you can produce different final states, and you can open up this process for lower energies, because then the threshold of the depends on the masses of the final products. In the other case, you won't produce pions. Here, you want just to produce electrons. And the inelasticity for this process is goes as the mass, again, of the final product divided by the mass of the primary particle. So it's much smaller than the inelasticity for the pion. Okay, so when I started the first day, I told you that it is important to understand, to compare energy loss rates in order to understand how different processes do compare one to each other, and to understand when a process becomes important with respect to another. So in general, when you have an inelastic process, you can write the energy loss rate as a function of the cross-section of the process. And so it will depend on the inelasticity of the process. That might depend on the energy of the target field. It depends on the cross-section for the interaction, the specific interaction to happen. And it depends, of course, as it was also for the inverse Compton, on the distribution of the radiation field in energy. Okay. Okay. So then for any process that we are studying, we can compute what is the cross section. Sometimes we can even measure it. We know, again, the distribution of the photon fields that are of relevance for the process, so we can fully compute what is the energy loss rate. And by comparing loss rates, then we can actually have an indication on how the different processes do compare with each other. In particular, so in this plot here, what you see are the energy loss rates for the two processes that I've shown you at redshift 0. So this is the pair production, which open up at lower energy, because you remember the threshold for pair production is around 10 to the 17 electron volt. The threshold for pion production is instead higher, so it opens up later in an energy range. But because of the inelasticity factor is much larger, and also the interaction cross section is so, then the pion production becomes rapidly the dominant process for protons to lose energy. And on top of that, there is always an adiabatic energy loss term that depends on the fact that there is the expansion of the universe, so there is an adiabatic energy loss due to that. Just to mention that sometimes you may find in the literature, instead of looking at directly the energy loss comparison, you can have comparison between the, let's say, energy loss length and or the energy loss times. So those are basically the same in different quantities related to the energy loss, as we have seen in the first lecture, that again allows you to make a comparison between energy loss processes, but the idea is exactly the same. So for the energy loss time, the faster is the process in losing energy, then the more dominant that process is. If we look at the energy loss length, this gives us an idea on the horizon that we have for ultra energy cosmic rays. So at 10 to the 18 electron volt, so this is the energy of the proton, the energy loss length is about 10 to the 3 megaparsec, and this mostly comes for this adiabatic let's say cosmological energy loss from the Hubble expansion. At energies of the protons of 10 to the 19 electron volt, the proton horizon is, so here is rather like 4 in 10 to the 3, 10 to the 3 megaparsec, and this is dominated by per production. And at higher energies, which is what you see also in the right plot there, so if we take protons of 10 to the 20 electron volt, then they can propagate no longer than 10 megaparsec, and this is when the proton pion production dominates. So you have an horizon. Also, we have seen yesterday that you have, and the day before, then you have an horizon in gamma rays, and the same is so also for ultra energy cosmic rays. So they cannot travel from very far distant sources, but they get absorbed by the fact that you start opening up, depending on the energy of the protons, new processes that destroy the primary protons. I won't go into the details of how to, ultra energy cosmic ray fluxes, but this is a big chapter in high energy astrophysics. So what do we measure of the highest, at the highest energies for cosmic rays? What kind of observables, what kind of experiments, and in particular, what is what are the possible anisotropies in the ultra energy cosmic rays. And whenever you have cosmic rays and you want to define what are the cosmic ray sources, the fluxes at Earth, you don't have to forget that you always have to propagate cosmic rays. So this one we won't see in this course. I won't touch upon cosmic ray propagations. I'm focusing on the photons and the neutrinos. But cosmic ray propagation is something that you have to take into account if you want to understand what are the fluxes of cosmic rays measured at Earth. So both in the galaxy and from other external galaxies. Okay. Are there any questions? Okay, if not, I'll start then with what's the question? Okay, with the other big part of the class, which is how matter does interact with itself, so matter-matter interactions. And this is specifically important because it gives us a way to connect different messengers, in particular photons and neutrinos. So we'll start from inelastic pp collisions. So those are processes where hadrons are mostly involved. So let's start with inelastic pp collisions. In this case, what you have is a proton-proton, mostly, interaction, which gives other protons or neutrons with the associated production of pions. So just a parenthesis, so pions, you can produce them through these proton-proton interactions or through the proton-gamma interaction that we have seen before, and this will be useful later. So this kind of interaction can occur, for example, in the galaxy if one is a cosmic ray proton injected by energy sources and the other is a proton from the interstellar medium. The interstellar medium is like the gas that is hosted by the disk, which is mostly composed by hydrogen and a fraction of helium. So you can eventually also have proton-helium interactions, but what we will see in this course is just the proton-proton. So again, for this type of interaction, there is a threshold. So in the proton target rest frame, you can derive what is the threshold energy for the cosmic ray proton to open up this reaction. Which is, if I use the pion, neutral pion mass, it's about 1.2 GeV. And this is in the proton target rest frame. Okay? So what I mentioned before is that through, and there will be, of course, as always, a cross-section associated to this specific channel, and this will give us the probability that this process occur depending on the energy and the kinematics of the particles. So there are then different mechanisms that can produce pions, either neutral or charged. And the production of pion is associated with two very important messengers, which are the photons and the neutrinos. So now what we want to understand is, given the different production processes for neutral pions or charged pions, how we can derive the final fluxes of photons and neutrinos and understand if they are connected or not, and if they are connected, what is the connection. So then we start from deriving one very important contribution to the photon sky, which is the contribution from the decay of the pi zero. So this is the main mechanisms that does produce photon, diffuse photon from our own galaxy from GeV up to at least TeV energies, okay? And we will see a bit that in more detail. So the lifetime of the neutral pion, just as a reminder, is about 2 in 10 to the minus 16 seconds, so it's pretty short and mediated by the electromagnetic interaction. So let's start to have a look at the kinematics of the process. So for the kinematics, you want to understand what is the distribution in energy of the final photons, because this is what you are interested in order to understand. Just remember that ultimately we're always interested in understanding what is the final gamma ray flux or photon flux that comes from this process. So let's start from the kinematics. So in the pion rest frame, what you have is that because of momentum conservation, the two photons are emitted back to back, okay, in the pion restraint. And the second thing is that by imposing energy conservation, you can get what should be the energy of the photon in the pion restraint, and this carries half of the mass of the pion, which is about 70 MeV. So all photons in the center of mass frame of the pion rest frame will have the same energy, and we will have the production of 2 photons per. What is the word before? Frame rest. So it's yeah, it's the pion 0 rest frame. So this is simple, is a 2-body decay. And we want to understand what is the distribution of then energies in the lab frame. So then let's go in the lab frame where the pion has a given velocity and a Lorentz factor, okay? So then we can get back to the transformation from the lab to the pion rest frame, where we can dub this angle theta star, the angle between the direction of flight of the pion and the outgoing photon. So from this relation here, we can see that there is a maximal and minimal energy that the photon can have in the lab frame, which depends on the sign of this term here. Okay, and gamma and pi is nothing else than the energy of the pion. So there is a minimal and maximal energy, and then we can also look at what is the distribution in angle of the photon energy. Okay. So now the question is, what is the energy distribution of the photons by averaging over all angular directions? So the pi 0 is a scalar, so the products are emitted isotropically in the pion rest frame. So then the angular distribution should be normalized to the total solid angle. So that with respect to the angle cos theta star, this is the angular distribution of the photons that you expect in the pion rest frame. Okay. Now by combining the different relations that we have written here, we can have a look at the energy distribution of the photons. Okay. And we see that the energy distribution of the photons is constant. So by expanding this last term here, you can check that the number of photons produced per unit energy in the lab frame, so this is the photon energy in the lab frame, depends only on the energy of the initial pion and the mass of the pion. Okay? And this basically constant at fixed energy. So this energy distribution is flat between. So it's a flat energy distribution between E gamma min and E gamma, so the minimal energy and the maximal energy of the photons that we have derived before. Okay, now. So when you have, like, for each energy of the pion, you basically have a flat distribution. So you have a box spectrum between E min and E max. Okay? And this is for one energy of the pion, but then the pion is not monochromatic. It will have an energy distribution that we will see depends on the distribution in energy of the primary protons. So this you will sum up different boxes to get like a bump, and we can check now what is the energy at which this bump is centered. So the center of this distribution is defined by the sum of the log of the maximal energy. If we look at this, is a log-log plot actually, and which is nothing else than the sum of the square root of the product of the two. And if you remember the expression for E min and E max, then the product you can derive what is their product, and you can check that the center in log scale of this spectrum is half of the pion mass. Okay. So regardless of what is the initial energy of the pion, the center of this flat spectrum box will be always the mass of the pion divided by 2. Okay. So this leads to what we call the pion bump in the gamma ray spectrum that is a typical feature of photons that are produced through pion decay. So yesterday I mentioned that the spectral energy distribution of a process can inform us about the process that has produced it, because if there is a specific feature, a specific characteristics that identify that process. And here for the pion production, this is the so-called pion bump. This is a spectrum of a supernova remnant, IC443, that has been detected by the LAT telescope, and for the first time, the authors have been able to prove that models for pion decay into the supernova remnant are better matching the distribution of the data points than other models. So this has been claimed as a smoking gun for proton accelerations in supernova remnant. So till the point where you don't find an evidence, observational evidence for this type of process, we were not sure if indeed supernova remnant could accelerate or not protons. Yeah, so are the ones that interact with themselves. This is mostly Yes, proton or photons, and then you have the pions, and then you have the decay. Okay. Good. Other questions? There was no hand. Okay, fine. Because so specifically for what I'm telling you here for this is that you are collecting photons only from the direction of the supernova. So this is what we call the region of interest. So when you do gamma ray analysis, you have to either point your telescope or select only the region that you are interested in. So this is a region of interest around the supernova center, which is that one. So you are already selecting, cutting out all the galactic emission. For example, you want to understand what is there are the different contributions to the cumulative photon counts that come from all possible sources of gamma rays in this region. So you see, you will have other sources that you have to model and to account for. You will probably have some diffuse emission. So what you have here, the red points, are already the data that are associated to that source specifically, okay? And then you can fit those data points with different models to, like here you have some Bremsstrahlung models, this pi zero decay, and in the past you could also have found some leptonic acceleration in order to understand. But you are already selecting, in this case, just the photons that comes from the supernova surroundings. For if you want to interpret the photons from the galaxy, then it's more complicated, because it might be supernova accelerating protons or also other sources. Okay. So then if we want, and specifically related to this, if we then, so this is the flux, if you want, is the gamma ray flux from a single source. So we just have one emitting source and we want to understand what is the gamma ray flux. So then the distribution of photons here is related to the distribution of the primary protons. What we can do is more generally to look at what is the pion spectrum from proton-proton interactions, and indeed to probe what is the link between the primary protons that have induced the gamma ray radiation and the photon spectrum, okay? So again, you have this proton-proton, it gives you pi zero plus proton, and then you have gamma-gamma. What you measure are the gammas, but eventually the first thing that you have from cosmic ray sources is the injected proton spectrum. Before, when we have studied this process, I've told you that the energy of the pion can be approximated with this inelasticity factor times the energy of the proton. And now what we want to understand it is, given a spectrum for the proton, for the protons, what is the spectrum of the pion energies, because this will be important to define what is the final photon energy distribution. Okay, let's then assume that the target is mostly hydrogen, and that the protons here are relativistic. So we can, as we did in the other lectures, define what is the local emissivity of pions. So this is the number of pions per unit volume unit energy, and unit time. And this is related to the target density of the hydrogen protons, so like the gas in our galaxy. And then we can approximate the energy of the pion through a delta function because of this relation. Okay. And we need to know what is the probability of the proton-proton collision to produce a pion. Depending on the energy of the incoming proton. Okay? So like any other process, you convolve the primary flux with the cross-section for the process to happen times the target density. Okay? So now then just expanding resolving for the integral with the delta function, the emissivity of the pions is 4 pi the target density, the differential cross-section evaluated at the energy of the protons, so the energy of the pion divided by the inelasticity, times the flux of the primary protons evaluated at the same energy, okay? So this is telling you that the local emissivity of pions produced by a proton population will have the same energy parametrization, the same shape of the energy distribution of the primary protons, but with energies that are shifted at lower values by the fact that you have, this is an inelastic process. Okay, so you can think, again, if I have a primary population of GeV protons, then I expect the pions produced at 1/5 lower energies, so the distribution shift, but the shape is basically like the same if the dependence on energy of the cross-section is shallow, okay? And so then from these protons, from these pions, you finally produce the photons. And the photons have like carry half of the energy of the pion. So once you have the local emissivity for pions, then you can go and look at what is the local emissivity of photons. I just re-put the units here. So per unit energy, unit volume, and unit time. And this will be the integral between the minimal energy that the proton can have, the pion can have to produce the energy of the photons that you are considering, times the integral over the pion energy of the spectral energy distribution of the photon multiplied by the local emissivity of pions. Okay? This we have already seen. This is the flat box spectrum of the photons from the pion decay when for different pion energies. This is the local emissivity of pions. Now what we are missing is to see what is the minimal energy that a pion should have in order to produce a photon of a given energy. And once we have it, we can perform the full integral. Okay? So then let's understand how okay. This will also be useful just to get first quantitative estimates, because if you are interested, I don't know, in explaining some gamma ray emission at a given energy, you should ask first of all yourself what kind of processes can enter, and so you can directly link what is the pion energy required to explain that gamma ray radiation, and so what is the proton energy. So all these little equations will help you to get quantitative estimates. You start working on some of these things. Okay, so we, again, just remember the definition of minimal energy and maximal energy. So the product is 1/4 of the mass of the pion squared, and you can also, in the same way, just quantify what is the sum of the two, which is the energy of the pion. And then with that information, remembering, so you can then solve for the pion energy, and you will get that the pion energy, the minimal pion energy that you need, gamma, okay? So this is the equation for the pion energy by solving this system of equation. And so for each pion, so for each photon energy, you know what is the minimal pion energy that you need in order to produce the photons. Okay? So we can then finally go back to the emissivity. You have a factor of 2 because you have 2 photons that are produced from the dn dE. The emissivity of the pion divided by this square root, which was in the expression of the photon energy distribution. So again, above energies of the pion bump, so once you are in the plateau for this term here, the photon local emissivity traces the pion local emissivity, which traces in turn the cosmic ray proton spectral distribution. Okay? So the photons carry the information about the primary proton population through these different convolutions. So above we can have a look here. So this is the map, the gamma ray map of the gamma rays that are produced from pion decay induced by cosmic ray interactions onto the interstellar gas, so mostly hydrogen. Again, you can see the projection in the galactic coordinate, longitude and latitude, and as we have seen yesterday, the morphology of the photons traces the shape of the target density. So in general, the gas distribution depends on the position in the galaxy, and indeed the shape of the photons field then will trace the gas in the galaxy, so the target proton density. While if we look on the projection onto the spectral energy distribution, so the flux as a function of energy, then we see this typical, so the pion decay are the green lines for different components of the interstellar medium. So if we look at the solid green, we have the pion bump at around 1 GeV, and then we have this power law at higher energies, which is linked to the power law of the primary proton population. Okay. So now that there are several ways to compute all this kind of emission. One can code from scratch all these processes through the equations that I showing you in these days, or one can use numerical codes that are out there in order to produce this secondary emission. In particular, there are two main codes for cosmic ray propagation and gamma ray production. One is the Galprop code, and the other is so one is Galprop from a US collaboration, and the other is the Dragon code, which is for cosmic ray propagation, and it has another module which is called Hermes for production of photon maps. Okay, good. So any questions so far? Ah, right, I just wanted to mention. So to conclude on this part, what I just want to show is how the real gamma ray sky looks like at GeV to TeV energies. So this is the full sky from the LAT telescope, and again in galactic coordinates, so longitude and latitude. Here is the galactic center, and you can already see that the most, by far, the dominant contribution to the observed gamma ray sky comes exactly from this proton-proton collision that then leads to photons. Okay, and the second one is then inverse Compton. Okay, now let's go to neutrinos. Because I mentioned before, you can produce in proton-proton or proto-photon interaction, you produce neutral pions, or you can also produce charged pions. So then the charged pions can decay into muons and muon neutrinos, and from the muons you still have two additional neutrinos that comes from the decay of the muon. So we want to now go to the neutrino flux and understand a bit of quantitatively. Okay, so neutrinos from charged pions. The lifetime of the charged pions is about 10 to the minus 8 seconds. So this time it is mediated by the electroweak force. And as in the case of the photons, we will start always from the kinematics, and then we'll go to the distribution, energy distribution, and then emissivity. So in the pion rest frame, again, we can now consider the fact that there is the momentum transfer is conserved. And from here, we can derive what is the energy of the neutrino in the pion rest frame to produce that gets produced. Okay, so the energy of the neutrinos will be of about 30 MeV in the pion rest frame. So now, as before, we go in the pion, so in the lab frame where the pion is moving. Where the pion has a given velocity and a Lorentz factor. And we compute what is the energy of the neutrino in the lab frame. I will drop the star for now, but it's the same angle as before. And we can show that the energy of the neutrino is related to the difference of the square of the masses of the pion and of the yes, correct, and of the muon, and it depends on the kinematic of the thing. Okay, so now, as it was before, you can define a minimal energy and the maximal energy of the outgoing neutrino, which depends on the angular distribution of the incoming, of the outgoing neutrinos with respect to the pion flight direction. Now let's consider that the pion is highly relativistic. Okay, and then we can have a look at the neutrino maximal energy, whatever. So the neutrino, the minimal and the maximal energy. Yeah, so let's have a look. Okay, so let's have a look at the maximal energy of the neutrino, where there will be a factor of 2 coming from here, and you can show that this is related to the energy of the pion. And if you define this term here in parentheses, whatever, as lambda, then, and you compute it for the pi 0, then, so for the pion plus, you can get that this is about 0.4. And so again, you see that, so in this case, while the energy, if you remember before, the energy of the photon was about 1/2 of the energy of the pion. In this case, the energy of the neutrino is, so the maximal energy of the neutrinos is about 0.4 times the energy of the pion, and so there is a range of variation. You can also compute what should be in mean, but in general, we can say that on average, the neutrino energy is about 1/4 of the pion energy. Okay. So similarly, for what we have done for the photons, now we want to compute what is the energy. So the energy distribution will be exactly the same. The energy will have the same shape. The energy distribution of the neutrinos. We can derive it in the same way. So let's start from here. We want to know what is the distribution in energy of the neutrinos. So similarly to what we have done for photons, because the final directions of the outgoing neutrino will be isotropic, we have this relation, and then we also have the relation between the differential energy and the differential angle. And so we can again derive what is the differential energy distribution gamma beta and with the relations that we have seen before. This can be approximated by 1 divided lambda in nu. I think is E pi, sorry. Okay. So then, as in the same way as for the photons that I have cancelled, okay, yeah, over there, we can do the same, but for the neutrino local emissivity. And for the neutrino local emissivity, we will have to consider again the same terms. So you will have this integral, the same, but at this here, instead of the gamma ray photon distribution, we have to replace the neutrino photon distribution, and we will have to compute the minimal energy for a pion to produce a neutrino of energy in U, which has the same derivation as for the photons. So we can then get to the local emissivity of neutrinos given a pion distribution. Okay, so again, as it was for the photons, the neutrino spectrum thus traces the pion local emissivity, which in turn is proportional to the proton density and to the proton energy distribution evaluated at yes, it was divided by, okay, I can't say, yes, there, k pi, okay? So in this case, the neutrinos again can carry information about the primary proton population, but this time, as I mentioned already before, the final neutrino energies will be shifted by even lower energies with respect to the photons, because as we will see also later, so the energy of the neutrino is about 1/20 of the average energy of the parent proton, while the energy of the photon is about 1/10. And this comes from this factor here for the inelasticity of the pion, and then the factor here, lambda, which is different by the simple factor of 1/2 that you have for the photon energy. So this is the spectrum of neutrinos of the, let's say, first in the first iteration of the process. So when you have the neutrinos directly associated with the decay of the charged pion, but then, as I mentioned, you can have. So this will be. So we have seen the derivation of the distribution of these neutrinos here at the first iteration, but then you will have a second decay of the muons in electrons and neutrinos. So if you want the total spectrum from neutrinos emitted by proton-proton interaction or charged pion decays, we'll need to also account for these other two neutrinos for the kinematics and the cross-section, in this case the decay rate of the muon. And if you want to compute the total neutrino spectrum, you have to add also the emissivities related to these other neutrinos. Okay. One thing that you can observe is that when you have this charged pion decay, besides neutrinos, you also produce electrons whose energy is linked fundamentally to the pion energy distribution and therefore to the proton energy distribution. So you produce if you want, through proton-proton interaction, you can produce secondary cosmic ray leptons, which will contribute to the cosmic ray electron flux and can also then have secondary gamma ray emission radiation, synchrotron, and so on and so forth. And if you just look at the flavor distribution of the neutrinos that reproduce through from PP interactions or from P gamma, what you have is that you typically expect a flavor distribution from these processes, which has one electron neutrino, two muon neutrinos, and no tau neutrinos, okay? So the flavor information is something that, if we have time, we'll see today, and that can help us discriminating between different emission processes. Okay. So here is just a plot of the intensity, so the particle flux as a function of energy of the neutrinos that can be produced from pion decay, from proton-proton interactions of ultra-high energy cosmic rays, where you see that you can have distribution of electron, neutrinos, and antineutrinos, and as well neutrinos and muon neutrinos. Okay, how do you measure neutrinos? So you probably know that at high energies, the instrument that is measuring neutrinos is the IceCube telescope in the South Pole. So it measures neutrinos at between 100 TeV energies and can measure different observables. So again, as it was the case for photons, you can take all your neutrino events and project onto different parameter space. So this is the energy spectrum of the total neutrino flux that has been seen by IceCube as a function of energy, which till very recently has been consistent with an isotropic distribution of neutrino events, and that can be interpreted as the neutrino flux coming from very high energy sources that are producing neutrinos either through P gamma or PP interactions, the things that I've seen here, and then neutrinos, because they do not suffer any energy loss or absorption mechanisms in the galaxy, so the universe is truly transparent to neutrinos, can reach us at these energies. And given the energies of the neutrinos, you can then point back to what should be the primary proton population in these extragalactic objects, which might be of different type, like star-forming galaxies or active galactic nuclei. So you can also do a fit to this data and arrive, with a parametric form, and then find the best fit values for this overall normalization of this flux and the power law index of this flux, and you can put your best fit contours depending on the data event selection. You can reconstruct what are the best fit parameters and then get back to your astrophysical models and check if this is consistent or not with what IceCube finds. You can also look, as it is the case for gamma rays, you can look at the arrival directions of neutrinos. So again, these are the magenta and the red are two different data sets that are differentiated by the techniques at which the neutrinos are detected, and you see that there is a given distribution of neutrinos, and you can then do some statistical analysis of what is the distribution of these neutrinos. Is this consistent with the isotropic emission? Are there excesses of neutrinos in the direction of specific high energy astrophysical sources? And these are current analyses that the IceCube collaboration does. And thanks to that, one big discovery in the last few years was the fact that there are excesses of neutrinos in the direction of specific astrophysical high energy sources. So in this way, you can claim like the first detection of high energy source neutrino emission. This was specifically for one galaxy, this one NGC 1068, and one transient AGN, which was nearby. But last year, what it has also been discovered is that there is a correlation of the neutrino events with the gas distribution in the galactic plane. Now, if you remember what I've just told you before, you can have also neutrinos that are produced by by pions produced in the proton-proton collision, where one proton is the target density of gas in the interstellar medium. And indeed, you can build models to derive what is the final neutrino flux and correlate these model maps with your real events. And a positive correlation was found with the neutrinos from the galactic plane. So there is like a 5 sigma evidence of neutrinos that come from cosmic ray proton interactions with the interstellar medium in our own galaxy. And it's not clear if what are the sources of these projectile primary protons. Okay. So one leverage that you can use in order to understand the origin of the neutrinos is the connection between photons and neutrinos. Okay, because in the end, all these processes can produce both final states. So now let's have a look in more detail on how you can connect photon and neutrino fluxes. So let's just remember, so we have P gamma interactions or proton-proton interactions. So in the P gamma interaction, you can produce photons from pi zero decay, right? But you can also produce neutrinos, neutrinos from when you have a charged pion. And eventually then electron, neutrino, and antineutrino. Okay? Then just to remember, so the inelasticity of this process is about 0.2, and the neutrino multiplicity is 3.5, and the gamma ray multiplicity is just 1, because you produce two photons in one of the two possible interactions. Yes, you're right. Okay, so at higher energies, this is not the only processes that can occur. You can also have, so as I mentioned, this goes through the delta resonance production, but at higher energies, the cross-section this process is mostly probable to occur opening up multi-pion production. So you will have at energies that are above the GeV, you can have multi-pion production. So you have pion, pi zeros, and pi plus and pi minus that are also produced. Okay, and the energy of the of the interaction, then sets what is the most likely channel to occur. And in this case, the inelasticity is a bit higher, 0.6. The neutrino multiplicity is 6, and the gamma ray multiplicity is 2, because you only have neutrinos from this pion, photons from that pion. Okay. Is the number of neutrinos that you produce per interaction. So you see here you have 2 charged pions, so from each of them you get 6. And here this can either go, it has 1/2 probability to go either from that in that final state or that final state, more or less, and then you can compute the final multiplicities. Okay. On the other hand, you can produce also neutrinos and photons through PP interactions, and it's basically the same. This will lead to proton and pi 0 that then goes into cosa ho scritto? Then goes into photons, and then on the other case you can have the production of charged pions and then decay into muons and neutrinos. Or likewise, you can have production also of negatively charged pions in this case. And the multiplicity of the photons is 2, and the multiplicity of the neutrinos is 6. Okay, so when you have this multi-pion production channel, basically you have the same number of pions that are produced per process, while in the p-gamma case, you have slightly more positively charged pion than negatively charged ones. So there is a bit of imbalance in the number of final pions that you produce. But let's have a look at the energies. At the energies then, which recalls what I mentioned before. So I will just write that quickly. So the energy of the neutrinos with respect to the parent proton is about 1/20 of the parent proton. And it is also about 1/2 of the photons, okay? So there is a relation between the energies of the parent proton, neutrinos, and photons that are produced through the same interaction. Now let's compare the yield, so the number of particles that are produced per unit energy and second, and this gives us then the link between the production rate. So let's consider the ratio between the number of charged pions to neutral pions that are produced. This is typically 2 for PP interactions and 1 for P gamma. This goes mostly through multi-pion production at higher energies, and this does not have assume that there are no negatively charged pions that are produced. Okay, then from the pi plus, pi minus, you produce 3 neutrinos. From the pi 0, you produce 2 photons. So if you then consider the yields, so let's have the energy of the neutrinos at the source times the number of neutrinos per GeV per seconds that are produced. Okay. This is about 3 times the number of charged pions times 1/4 the energy of the pion times the yield of the pion, and the same you can do for the photon. Okay. And then from these two relations and the definition of the ratio, you can derive that the neutrino yield is related to the photon yield directly. Okay, and this is the in a very simplistic terms, the connection between neutrinos and photons that comes from P gamma or PP interactions. So depending on the primary process that is producing photons and neutrinos, the relative yield between the two is gonna change. So it does mean that if you have a population of high energy sources that is producing a neutrino flux, so in particular the one that accounts from this diffuse neutrino, high energy neutrino signal, then you inevitably have also photons that are produced. So depending then how far these photons can travel, so if they don't, let's assume they don't get absorbed because they are local by the pair production, then you also do produce an associated photon flux. So one of the paper of today is exactly about that. So if you want to have a good explanation for the neutrino, ice cube neutrino diffuse flux in terms of astrophysical sources, then you have to be careful not to overshoot also gamma ray observations that could come from the same neutrino population. So this is a very minimal ansatz on the gamma ray flux. It also ignores that you can have contribution then for paid cascades, and it is under the assumption that both neutrinos and photons can escape the source. Okay. Is there any question? Okay. If not, then we can. Yeah. Mm-hmm. Or you measure them at different energies. So so that's that's a big. Yeah, so there might be a lot a lot to talk about because the problem of the cross sections, so the uncertainties on the cross sections for cosmic ray secondary production is a huge source of uncertainty in the prediction of the final fluxes. Because as you said, you have to, so typically we can measure these cross sections, but we have access to cross sections only in a limited range of energies, either too low, either too high. So there has been a lot of effort in the community in the past years to push experimental collaboration to measure the cross sections that are affecting the most cosmic ray propagation and final photon and neutrino production at the energies that might be of interest for this kind of process. If they are too wide, you don't have access to them, you have to rely on extrapolation. But we are at the stage now where measure could be possible. So we need input at energies that are achievable in the lab, but for which there is no experimental setup to do so. So there is a huge program to try to do these cross-section measurements and to find phenomenological models to then interpolate or extrapolate or whatever. But yes, and then if you have new physics, of course, this will enter eventually in these cross-sections, so might have also an effect that we at the moment we don't know how to include. The equation of state. Okay. How can yes, you have quite a few feedback reactions on the medium. Yeah. Yeah, sure. That's why it's complicated, right? In the sense that these are the lay down of the basics of how you produce photons, but you don't have to forget that you are in a medium, so you can have you can have reionization of the medium, you can have other effects, you can have back reactions, and whenever you then go to real data and you want to interpret them, you have to count everything you know. So you're not allowed to leave out things that you think are there, but perhaps are subdominant. So point is how you model then what you don't know, and that's all the game, right? Learning something about the fundamental interactions of matter with radiation. Yeah, perhaps we can discuss later, but indeed it's so the what we can do in the last 5 minutes is to have a look at the flavor composition of the neutrino flux, because as I mentioned, we also can distinguish between electron, muon, and tau neutrinos, and this is possible experimentally because the three of them leave different morphologies of the event in the detector. So IceCube can distinguish between the three flavors, although cannot distinguish between neutrinos and neutrinos. So the flavor composition of the neutrino flux has been used as an important observable in order to get back to the production mechanisms and also for new physics searches. In order to understand what is the flavor composition that we do expect, we don't have to forget that neutrinos are produced in high-energy astrophysical sources, but then they have to travel to Earth, and when traveling, they inevitably oscillate. So in order to understand how to go from the flavor composition at the source to the flavor composition at Earth, we need to recap a bit neutrino oscillations. Yeah. Okay. So we can work in the two-flavor approximation. This is in all textbooks, but if you have, so you remember the mass state and the mass eigenstates and the flavor eigenstates of neutrinos are not the same. So the electron neutrino is related to the mass eigenstate nu1 and nu2 through a mixing matrix. Okay, so you can define this mixing matrix U and generally write the neutrino of flavor alpha as the sum of the mass eigenstate multiplied by the mixing matrix. Okay. So if you have let's suppose an electron neutrino that is produced at time t0 and at position x0, then you can look at the time evolution of its quantum state, and this will be related to the mixing matrix and to the mass eigenstates. So there is a final probability of a neutrino, an electron neutrino, to oscillate in a muon neutrino at a given distance L from the start of the observation, and this one can show that is proportional to the square, to the sin square of twice the angle times the sin square of the differences between the neutrino masses and 4 nu. Okay? So this is the phase phi of your oscillation, and if we use the values of the difference between neutrino masses measured by observation of solar neutrinos, we can get, we can quantify what is the value of this oscillation phase. Okay? So given the by 7.4, 10 to the minus 5 electron volt squared, times a distance in parsec. So we explicitly put the energies of the neutrinos at the TV scale and the distances in parsec, because we want to understand what is the impact of neutrino oscillation on astrophysical scales. So you can see that if you have an energy of the neutrino of about 100 TeV, for typical distances of the sources of megaparsec scale, then this phase quickly explodes, so it becomes huge. It's about 10 to the 10. So it means that only phase average observables make sense when we are looking at oscillations of neutrinos in astrophysical environments. So in this case, the oscillation probability takes up a simple form also with in the full 3 flavor case. So averaging over the phase, you can write more generically that the oscillation probability from the flavor L to L prime is the sum over the 3 flavors of the mixing matrices okay. So if you then define f of L0, the flavor fractions at the source, so what is the flavor fraction that a source is producing, such that they are between defined between 1 and 0, and the sum of the 3 is 1. Then you can rewrite the flavor fraction at earth as the sum over the flavor of this oscillation probability times the fraction at the source. So this is the fraction, the flavor fraction after oscillation. So now let's remember from PP and P gamma interaction. What we said before is that we produce 1 electron neutrino through 2 muon neutrinos and 0 tau neutrinos. So more in general, from like astrophysical standard processes, you have that the electron fraction is 1/3, the muon fraction is 2/3, and the tau initial fraction is about 0, okay? So then you can rewrite your initial fraction of f mu and f tau all as a function of the same, of one of the three, most notably the electron neutrino fraction, okay? And then if you go to into the expression of the final after oscillation flavor fraction, you put in this expression for the probability conversion the measurements of the different mixing angles that we measure thanks to neutrino experiments. So we have measurement for theta 1,3, theta 1,2, and theta 2,3, and perhaps an upper limit on the theta CP. So you can plug in the numbers, and with the measurements of the neutrino oscillation angles, you can show that the final fraction of flavors, so a third, gets redistributed, and all neutrino flavors gets the same fraction, a third, which is 1/3. Okay. So what you do expect from this kind of initial distribution of flavors is that the flavor distribution get then equal once you detect them a third. Okay, so this is what you can see in this plot. So this is a tertiary plot. When you have the three axes, you have the fraction of the neutrinos electron, the fraction of the muon neutrinos, and the fraction of the tau neutrinos, from different astrophysical processes, what we expect, for example, from pion decay, which has these these flavor ratios at the source, you would expect a redistribution of 1/3, 1/3, 1/3. So this will be this point more or less at the center. Then you can complicate things. You can consider other processes for neutrino production, look at their flavor distribution at the source, redo the calculation of the final flavor fraction through the probability of oscillation, and these are different models for neutrino production and what is the final flavor distribution that you would expect a third. And here in blue are the contours that are currently measured by IceCube, so which are not very precise. So at this moment, the flavor information can discriminate between, so for example, can exclude some of the processes for neutrino production, but cannot yet achieve high precision analysis in order to pinpoint what should be the specific production process. So one of the, just to finish, one of the interesting thing is that if you just consider, so you might know that one of the big problems of ice cube is to get rid of contamination of atmospheric neutrinos, so that the neutrinos that are produced from the interactions of protons within our atmosphere. But if you look at the oscillation probability and the oscillation phase, if you put then typical size of the oscillation scale of order of the kilometers, then you realize that from these kind of atmospheric neutrino, you do not expect tau neutrinos, because again, tau neutrinos, you don't produce them in pp, and you cannot oscillate, you cannot produce them from oscillations. So tau neutrinos are really the smoking gun for the fact that you have astrophysical sources of neutrinos contributing to the neutrinos that IceCube detects. Okay, so for today it's all, and we'll meet in the afternoon for the exercise. Bye. Ciao.